Okay, so these notes are a little bit of a review on the sorption, but also an important problem that I want you to see at the end of it. So real quickly, let me go over sorption again. So sorption can be from the air to the solid phase. Here we see something in the that is absorbing to activate a carbon surface, or here we have something in the water phase and it's absorbing to the soil, or sorbing, which is a combination of adsorption and absorption. Why does it occur? Sorry. Why does it occur? Well, the molecules are tending to lower their energy. So if it's a hydrophobic molecule, it takes a lot of energy to hold it in the water. So the hydrophobic energies will tend to accumulate out on a surface, or better yet, will try to partition into that organic matter. So here we see a molecule both going matter here and accumulating here. So absorbed and adsorbed. Together, that's sorbed. So we talked about models. The most common one is linear, where the concentration in the water or air phase is in the x-axis, and the concentration in the sorbed phase, which we could call C sub s, but often we see it as a small q here, is on the y-axis. And as we add higher concentrations with the same amount of soil, we'll see the sorbed concentration go up. The slope of this line is the distribution coefficient, the Kd, or sometimes it's called the Kp, and this is simply the linear isotherm. The units are a little funny. I mentioned that in the PowerPoint notes. So the sorbed concentration, remember, is mass of chemical per mass of solid. So this would be like milligrams of trichloroethene per gram of sand. Concentration is what it usually is. It's the mass of a chemical per volume of water. So it should be actually length cubed here, sorry. So gram per liter, sorry, yeah, gram per liter there. And Kd is then inverse of the aqueous volume over the solid volume. So it kind of has the units for the chemical are buried in there, because it's the concentration of the solid over the concentration of the liquid, but those two contaminant concentration or masses cancel out, so you end up with like a volume per gram. So this is volume water per gram of soil, or gram of carbon, or something like that. So these relationships are called isotherms, remember, and there's some other isotherms. So here's the nonlinear versions. One we saw before, which was the Freundlich isotherm here. That has the sorbed concentration. It has a distribution coefficient, or it's a little bit different than the one before, so we'll call it Kf for Freundlich. And then really what makes it different is this exponent, 1 over n. So this exponent is usually less than, gives it this kind of curvature, but it doesn't quite get flat at the top. Now if it does get flat at the top, like over here on the right, we didn't talk about this in the PowerPoint, but there's another one called the Langmuir isotherm. And we see that one with gases a lot, so you'll see it actually flatten out. When it flattens out, it means there's just no more space for the chemical to accumulate on the solid. So it's usually for surface or adsorption reactions. Chemical and the solid. A little different than other things we talked about, like vapor pressure or solubility. This one you need to know two things. You need to know what the chemical's like, and you need to know what the solid's like. So as I mentioned before, they've tried to come up with ways of getting sorption by normalizing, and they usually tie carbon on the soil, so that this coefficient here is a function of distribution coefficient for organic carbon, and then you need to know the fraction of organic carbon that is in the soil. So they do this by ignition test. They just actually burn the soil, and they can tell how much carbon burns off of it. But KOC, how much it absorbs to that organic carbon, is also not really well known. So what they try to do is tie it to some thermodynamic properties that we mentioned before, like the octanol water partition coefficient. So that when you get that from a chemical by placing it in water. So it's dissolved in water, and then you throw some octanol in there. So the octanol and water are two separate phases, and you shake it up and see how much shows up in the octanol. Or sometimes it just goes by the solubility of the chemical as well. Both of those are sort of surrogates for the hydrophobicity, or how much that chemical wants to be out of water, which means how much does it want to sorb. Okay, so let's try a problem now, and let's just stick with the linear isotherm. So how do they get these values? This is a sort of isotherm sampling. So you sort of picture yourself in the laboratory for this one, and you've got a 10 milliliter vial here, and you're going to fill it with some soil and some water, and take a syringe or something and spike in about 100 micrograms per liter of TCE. So you could do the math on 8 milliliters of water and how much chemical you'd need to put in, but you'd have a target concentration in mind. And then you let it mix for a while, in this case maybe for a pretty long time, and you see that it's lower now. So what happened? Well, some of it sorbed to the soil, right? So the total TCE that you added, you can do from time zero, right? You have 8 milliliters times 100 micrograms per liter with some conversion. Overall, you put a total of 0. Actually calculate it from the difference. So you know how much you added, 8 micrograms, and you know how much is in the aqueous phase, because that's what you can measure. That's the 63 micrograms per liter that you measure at the end of the experiment. So all you don't know is this one. So we'll put a question mark there. That's the one you don't know. So you know 2 out of 3, so you can figure out the other one with a little quick math. So you have the total on the left, 8 micrograms. You have the total in the water phase on the right, 8 milliliters of water times the concentration times some conversions to get the units right. And you know how much soil you put in, so you put that 2.5 in times the concentration on the soil. So remember, Q's units are mass of TCE per mass of sand. So the mass of sand is 2.5 grams. So everything is known except for that Q, and you solve for Q, and you get 0.12 micrograms TCE per gram soil. So KD, if you only have 1 point like this, it'd be better if you had 4 or 5 or 6 or 7 points, and you'd make a line at different concentrations. But if you only have 1 point like this, you can come up with a rough estimate of the KD. It's simply Q divided by the C at the end of the experiment. So that's 0.12 divided by, I think that should say 63, not 23. I'm not sure how I got that 23 in there. Yeah, that should be 63. So my numbers are messed up. Sorry about that. So put that number in here, 63. You'd have 60.12 divided by 63, and you would get, let me see real quick, get it for you. You'd get 0.0019, so you'd get 1.9 milliliters per gram with the little conversion here. So see if you can follow those numbers. This is a good way to know that you understand sorption. Remember, the bottom line is you add a known amount to the solution. You look at the long-term aqueous concentration, which is measurable, and then by difference you figure out how much was on the sorbed. Now, there's all kinds of details, like you'd have losses through the bottle cap and things like that, but you could sort that out. But for now, just keep in mind this mass balance up here. And this is how you get to see how sorption happens.